point that I want you to live with is you have some sense of the things that you will need in order to do the proposals that we discussed, right? Soon enough, there will be a call for proposals. Soon enough, you'll be asked to write not only a science justification, but also how you want to carry these observations in order to meet that science. And he's gone through a lot of details already. I will stress some other points, and including something, starting an exercise, and then we will continue tomorrow, the day after tomorrow, and so on. And of course, this is a very short overview of very few selected points. The operation of a big telescope, a complex telescope by DKIST is really huge, and I'm not doing that many justice. And for example, this guy here is the DKIST operation scientist, right? I think that's your name. So that she knows everything, and she's working on all of them. So this would be the 4 points that I will touch, especially the first, a little on the second, and then some glimpse of this. In particular, the data thing will be discussed in much more details on Thursday morning by the people that data center. But I did already said that the data will be transferred from telescope to over, and there will be processed and massaged, whatever here. Okay, so which observations? You have to decide what is your science and what is your preferred diagnostics, and Phil did a good job in explaining you why certain diagnostics tell you certain things, and why you should use them. So the first thing to do is choose your wavelengths, plural, and instrument, plural. And then, of course, which field of view will satisfy your science, which cadence resolution, and so on and so forth, and choose your parameters. And I'm fairly sure that all of you are familiar with iris. Who is not familiar with iris? Nobody. You're not familiar with iris.
So what do you mean by familiar?
Have you used it? Have you tried to propose some data? No? So who knows what this means? Only one knows what that means?
That's not realized.
Wow. Really?
It's the observation.
You know why these numbers? You choose, this is a very, I don't know how to describe it. It's like a binary thing. Every digit of this number means something. It means that you're using, say, the 4 slit jaws instead of only 1 or only 2. That you're going with a certain cadence for the 4 slit jaws. Or that you're using the long slit of it, or that you're reading only a portion of it. That you're getting the full spectrum or only a certain subset of the spectrum. That you're bleeding or not, and so on and so forth. Right? That you can do a very large coarse raster like this says, so that you have a slit that moves with big steps, and you cover a large field of view, but of course it's very far away, and blah blah blah. Right? So if you, again, by now it's easy. You just go to the Iris web page and you pick whatever you like. Right? So I can use that data. Right? But if you were to propose, you have to define all of these differences. That will be translated in numbers, probably by Python too, because it's every machine. The one thing enters here and the number comes out there. So unfortunately, the case will be like this and more. It will be more complex because we have not only one spectrograph and the slit jaw images that go with it, but we have 5 instruments, of which 4 can work together, as we have been described. We have a larger selection of spectral ranges that we can do, depending on the instruments that you're using. Also, you have to decide your binning, if you want to use it or not, your field of view, your cadence, and your polarimetry. These are all polarimeters. Just beside the BBI or CPM here. So it will be an effort. This is like a table view of the instruments with the names, the acronyms, so maybe you don't need to put it there. It's in your Google Drive. The wavelength range that they can access, And DKIST for now goes from 390. This is a hard limit. This is the 5 microns. It's not a hard limit. It can go all the way to 28 eventually if we have the proper instrument. For now, the instruments stop at 5 microns. And these are the kind of instruments they are: imager, polarimeter. This is an imager that does spectroscopy and polarimetry, and this is a normal spectropolarimeter, and these are some analogs. I don't want to go into the details. There are some very detailed summaries of all their performances, and if you want them, they are both in the folder and down the table down there. And now, before I go into some selection things, do you have clear how these instruments work? You know, the fact how the spectra, you know, you have a slit spectrograph, and you have 2 slit spectrographs, 1 and 2. And they just acquire a spectrum along the slit, and if you want a larger field of view, you don't have to move. Yeah.
So you have a range of wavelengths you can see with different instruments.
Yes.
There are very specific lines.
Yes.
So you can always see those lines?
I'll get to that. So, okay, these are normal spectropolarimeter like the one on Keynote. You know, are you familiar with the one on, oh, even Iris. Iris is the same, but you add the polarimeter. This is like the first. This is probably the one that people are most familiar nowadays, or it is on the DST. It's based on Fabric.io, and so it produces monochromatic images, but then you can tune it. So instead of sending it to the view, you have to go away. Right? And if you want to have movies and so on, I just don't want to overload people now. This is a simple imager, like a slit jaw on Iris. This is a bit more difficult. This is one of the new things in solar physics. They have been using them in nighttime astronomy for a while. This is a device that allows you to have both spectrum and coverage of a certain field of view, 2D field of view, not just on the slit at once. It's essentially a trick, because you take your image, you slice it in certain ways, whether with fibers or mirrors or whatever, and then you rearrange these little pieces along the slit, and then you have spectrum. Of course, you paid because the instantaneous field of view is rather small, because you can fit like 3 million pixels in one slit or even more. But anyway, we can discuss this later if you wish, or if I have time at the end, I have movies to show how these things are. So, to your question about the spectral range and how you work on those, right? Valentin already, I think he showed this picture plus some more, and again there are tables down there. So this is ordered in wavelength from the blue to the red, and these little lines are the actual wavelengths that are accessible with that image. So only a certain discrete number of lines are accessible with certain instruments. There would be 4 in the BBI, the blue channel. There would be another 4 in the BBI, the red channel. The VTF also can access only discrete ranges, and for now there are 4 pre-filters. This could be pretty sensitive in the future. The DL nurse.
This is the reason that you need 3 filters.
You need 3 filters, and again I will.
Well, certain time range.
Yeah.
But if you don't have a 3 filter, you won't work.
Yeah, I will say something. I think that also Serena tomorrow will say something about it, and we'll say. I mean, this is a broadband imager by definition. Is that a sort of a pre-filter with a band which is of the order of, it depends, it can be 50 angstroms or more than that, or less than that. Say what?
There are all wavelengths.
Yeah. Yes. They are all in that table if you want, but I know them by heart by now. So one is the sodium D line, D2, I think. No, D1. Or D2. One from the red. That's the D1. Then there is a 6302, which is a photospheric line for magnetic fields. Then there is H alpha, and the calcium 2 infrared 3. No, only the 85 for you. Only one of them. And the same is true for the Gianna. Yes, Phil.
Just a comment. It makes it look like short wavelengths have very limited capability, but in fact, the
No.
density of spectral lines increases to the blue.
Yes.
So there's actually very few lines in far infrared.
Oh, I see. We should use a log scale instead of a linear scale. That's what we
I
said.
just want to point out that
Oh, that's a good point. That's a good
no, I
point.
mean, there are a hell of a lot more lines
Yes.
in the atomic lines, molecular lines with
Gotta go, yes.
so if you're going to do atomic spectroscopy, the X VBI is going to, the WISP is going to like almost none. The does, but that's not true.
That's not
Because
true.
the density lines decreases as well.
Yes, and actually I think that there will be an exercise tomorrow or maybe Thursday where you will actually go to the atlas, and so you can explore the atlas and see that it was right versus going towards the blue or kind of things. So you're perfectly right. Yes.
In fact, it gets so bad that the ultraviolet.
That it will
There's
get
no way,
continued.
it's just a haze of.
Yeah. Yeah, and that has consequences. But anyway, so the same is true for the DL-NIRSP that has a larger number of pre-filters, so spectral ranges. And then, as Valentin showed, the cryo-NIRSP has these 4 pre-filters. This is a trick because within this pre-filter there are 3 lines, 2 iron 13 lines, and 1 helium 1 line. So this, you can get multiple lines within. The DISP can access the whole range, right? And you have to select how that happens. That's another, granularity that you have to think. The VBI blue, the VTF, the VBI red, that are the imagers, they can do one wavelength at a time. So if you want multiple wavelengths with them, you have to see it. The VISP can do 3 spectral ranges at a time, and you can choose them as you wish, almost as you wish. There are some mechanical issues. At some point you might bump against things, and not everything would be available, but almost everything would be available. The DL-NIRSP has 3 arms, and so you have 3 ranges at a time, but these 3 ranges are predetermined for you. You have to choose among things that are offered. You cannot do it. I guess that you could convince someone to buy another refrigerator, but maybe not. So maybe again to your question, Jenny, that the VTF has a discrete selection of lines, uses a pre-filter wheel to select the line, and the selection of these ranges lines happens within seconds, and the sequential wavelength is built into operation. So with the VGI, you can do the Cauzzi K, and then G-band, and then H-band, and then something. That is part of how they work. Oh, I switched them, but it's the same. It's the same idea. The VTF is the same as the VGI. So that you have a pre-filter wheel, and you continuously turn the thing, and you turn it online, and the next, and the next. The DL-NIRSP and the cryo also has these relatively narrow pre-filters that also in a wheel that in principle could also be selected rapidly, but this multi-wavelength sequences is not part of the normal operation because you have to move with only so slightly the cameras with respect to a given position, right? And so there you enter into the issue of repeatability, which might be delicate. Including the fact that you don't go back to the original position and then your calibrations might not match with what you thought. So these ones are meant that you, today, or at least a good fraction of today, you will observe with this equipment. If you want to change it, tomorrow we can do it. Or maybe next year. The VISP is yet another thing. It's very versatile in the sense that you can select any of these 3 spectral ranges, but it's a spectrograph, and you have to eliminate the overlapping orders, so you have pre-filters as well that are much broader, and these are positioned semi-manually in front of the cameras. So this is not something that you want to do in any rapid times. So this is certainly something that you do one day to the next. So if you have a great science that uses 6 lines and they must close her with this, you gotta think how to do it 1, 3 to get it into 1. Okay. Any questions here? So, yes. This was about 10 angstroms, so 1 nanometer. So they are very narrow on the camera. All of our instruments, spectrographs, are polarimeters, and they are all dual beam. So that means that they take one state of polarization and needs orthogonal one at the same time. And there are various solutions. The DISP images them on the same camera. So essentially, you cut out of your camera in the spectral correction. Right? You would cover 20 angstroms, but 10 must go to the I plus Q, and 10 must go to the I minus Q. And I think it is the same for the next I think so. And also for the pi. The only one that is different is the BTF, which has a second. So they keep their field view. Which is the next object. And I think Valentin already showed this, so I don't need to stress it too much. This is the field stop of the Gauss, so the Gregorian focus is 2.8 minutes diameter, so the inscribed square is 2 by 2 minutes. And this is the maximum field of view the sum of the instruments can sample, because their optics are built just so, without recoil. The instantaneous field of view is smaller than that, but as I will show in the next slide, they have tricks to cover larger field of view than the instantaneous one. So the field of the BTF, I actually was told that it is 1 square. So that is a 60 arc-second diameter circle. This is a VBI, 45 arc-seconds, VBI red, 70 arc-seconds, and these are the three arms of the disc that are of different length slits. And this is the DL nerve. You can see this is the coarse mode, so lower resolution, middle mode, and you might not notice, but there is one in the very middle, which is 2 arc-seconds. 2 arc-seconds with red resolution. So those are the instantaneous field. Yes?
In reality, the right image will be one inside the other, right?
Yes, yes, this is important, and I have another slide later on. You are absolutely right. They all coordinate, and this is cool. You cannot look one thing with one instrument and another thing with. So as I mentioned, some of the instruments, in particular the VBI and the DL NERSP, has a mechanical way to either translate the camera or to move the image a little bit with a mirror, so that they, without repointing the telescope, they can sample the whole thing. So it would be like this. This is the blue, VBI blue, 9 tiles to do the full 2 minutes. 4 tiles to do the same for the red, because the scale is different. This is the DL NERSP in the mid resolution, about 20 by 25 tiles. And just to give you a sense, this is the sun, right? We're talking about this. Let's remember that. And this is with the DL NERSP with a coarser resolution, so lower spatial resolution, of course, more light as we must. The DL NERSP could do it also with the smallest field of view, but that would take forever, right? Because it's 100 by 100 tiles to cover the whole thing. And of course, as you do this game, your skin is punished. So this is one of the many trade-offs that you have to take on. Do you really care about those 10 seconds, or do you prefer to have a full dark minute? I don't know. It's up to you. Well, flexible. The spectrograph like this and cryo will just do like what Iris has. You position the slit somewhere and then you scan it and you run. With a certain step that you can choose. So that's very, very fancy. The same is for the cryo. And before the corona, people go crazy, and Valentin already showed this. And for the coronal case, cryo can access a bigger field of view. So the field stop is 5 minutes in diameter. And then you can sample this with a different configuration of cryo that has a longer slit. It's a 4 minute long slit. And you can raster the field as you wish. I mean, you can go further than here. It's just that your slit gets shorter and shorter because you are in the field stop. Okay, so this was a lot. Of course, you won't remember any. There are the tables. For every instrument, we have a so-called instrument performance calculator that does most of this for you. I mean, you enter the input and you see if the output is okay. So he will be giving like steps 0 of this kind of exercise this afternoon for the flux budget of the telescope instrument. Tomorrow, I will be describing one of these instrument performance calculators. We have them for every instrument, but we don't have time to go through all of this here, and I think it will be also a little too much. But I will be describing the DISP, and you should be able to use it also because, as he already explained, the DISP might be one of the first instruments offered when there is a call for proposal. You might not have them all, but probably when the call goes out, there will be DKI and DISP. DKI is relatively simple, there's an imager, not much to choose. This might require a little more, so I'll give you that information. So we have them for the nurse, for cryo, for DKI, for DKI, and so on. Okay, so now let's go to how these are each instrument by itself. How do they work together? And again, the cryo, you already explained, is essentially standalone, mostly because of the cryogenic issues. And these other 4 can work together with UVO. The most important thing is how to split the light between the instruments, how to point, and is there any instrument that's more important than another or not. So, how to split the light. You can do it in many ways. The solution that was settled on is written here. That the light will go, at any given wavelength, the light will go only to one instrument. It will not split, say, 50-50 or anything like that. So if you're doing calcium K with DDI, you cannot do calcium K with anything else. And so on and so forth. The second important thing to remember is that it is much easier to fabricate a beam splitter that splits also wavelength of the light that reflects the blue and transmits the red. So that essentially the flow is like this from the telescope to the instruments. Some blue is reflected and the rest is transmitted. Some other, of what's left, some blue is reflected and the rest is transmitted. So it cascades down. And depending on where you position these beam splitters, you can obtain any kind of configuration you want. I mean, you can take them all off and give everything to the dealer. How do we play around with this? With this another instrument called another tool that we have, which is the FIDO that Valentin was discussing, and so now I need your help. So first of all, let's see. These are the beam splitters that we have. So you see one reflects all the way to, I don't know, reflects all the way to about 480 and transmits the rest. The other one reflects to 560 and transmits the rest, and so on. So who has a good science case they know about? So we can try and see if it works. You want to do imager with a DDI in which we want to have G-band, like, then did you have your context? That's right. Okay. G-band by itself, it says, okay, success, because that's the only thing we have. So, how about we go to the DISP, and we want to do, I don't know. The DISP, you can choose any wavelength, really. There are a few already preset, but you can pick. So why don't you want to do H gamma, which is one of the Balmer series that's good in flares and light, right? It's actually the only instrument that will be able to do it, because we don't have filters or H gamma in other instruments. And here, yes. So you start and you have a problem, you see. This is not a success for this instrument. You can probably change if you put the weight here, you put 10 here and 0 to the other one, and so on. You know, so you want to give priority to one instrument instead of another, and how you do that. Say, if I can choose, I'd rather this way than go to this way in this instrument rather than another. But that's okay. Then you want to do, say, Algin 2 with the VTF. That should work. Success here. And then you want to do Algin 2 also with the others. And the answer would be no. Actually, I don't know why, but it gave priority to the others rather than the VTF. So it did it for me. I guess that the combination of the instruments becomes more and more restricted. So, and if you wanted to do like another one, let's see. So this one won't be there. I don't know if that will work. No. So see, this wavelength in the DL nurse and this wavelength in DDF are close enough that the things will not work. That's one. Make sense? And if I can speed up or anything, I don't know. Okay, so we went through this. So this is to your question, Lily. They all co-point. Whenever you point the telescope somewhere on the sun, they will all co-point like this. So the center of the field of view of every instrument is the same. Of course, yes. Well, you mean you repoint the telescope? No, what do you mean by changing the situation? Yes, that will be discussed this afternoon. Yes. This is the optical center of the field of view of the instrument, correct? Okay. So, yes, and then the fact that at times the difference of where the blue is located with respect to the red might be important. Yes, and so that would be.
You have 1 hour.
There is an exercise. It's all this fun. Yeah. So as he mentioned already, the Coudet table rotates. So you don't need, by now we're all used to say, this is solar north, this is solar east, right? That's what we think when we see an image. It doesn't need to be. It's convenient, but it doesn't need to be. And one of the things that you can do is certainly rotate the Coudet table so that you orient it differently. For example, if you're going to go along the pyramid. But then again, you rotate one, you rotate them all. Okay. So, let's see. Every instrument co-points, we already said that. After, maybe I should have put this early, each one has their own references, their own parameters. You can and probably will start them all at once, but then they go independent. There is no correlation between what one is doing versus what the other is doing, unless you want to point somewhere else, of course, other stuff. And no one of the instruments drives any other, but in your proposal, you can specify which one of the instruments you really want to complete. Right? Maybe the first instrument would take 2 hours to complete, the second would take 2 hours and a half. Say, okay, complete the first. Forget about the second, or vice versa. There would be. Okay, so I think I'm almost. So the next thing that I wanted you to remember and do something today is this one, about the proposal cycle, since we're getting close. We need to give you some information in how to apply and what to expect. So how to apply, there is a proposal tool online, so you will be working online. And in this tool, you will have to input all the necessary fields to define an observing program, like that big long number of iris digits. They are not all the same, but that is an idea. And of course, there will be guided answers in the form about what you want to do. the thing exists. Alexandra is there, she is the main responsible. That's a good word, responsible. It's still in the development phase, so it's not fully finished, it's not fully functional, right?
It is functional, but not all the requirements are.
Okay, but it is good to give you an idea of what will be required. Actually, this is the first group that has access to it. So the idea is that you will try it and you will give feedback, and then again, I don't know if that's good or bad because you will get a lot of feedback. Being Joe, which is the software engineer that is working on it, say, please describe it as a chalkboard or a whiteboard, right? You are going to get in, you're going to do things, writing, and so on and so forth. After a month or less, everything will be erased. So this is not your final proposal. This is not what will give you time to do for the parents. You will have to do a formal thing for that. But you will learn experience. As you. So this is the website, and it's in the folders, whatever my presentation is. You just click on register. You get an email that says confirm or whatever you want to say. One little quirk that I was just told is that if more than 50 people try to register in a day, the registration is closed for that day. It will resume tomorrow. It's some sort of anti-spam thing. So maybe some of you will be left out today, but you can do it tomorrow. And then we will go through the exercise in a couple of days. So this is an example of the fields that you will have to fill in. And then what happens after you apply? Is any of you familiar with applying for telescope time? No, not at all.
Well, but really depends, right?
Yeah, it depends. I mean, some of
The solar telescope on the Canary Islands is trivial versus ALMA.
Yeah. ALMA is a pain, and actually I think that we are approaching that kind of pain. In the sense that, in the middle, yeah, no, not as bad as ALMA. So the cycle is 12 months when there is a solicitation window. Let me go with the others. So the first one, there is the call opens, and you have to submit something, say, within a month. I think that would be the typical kind of interval that would be allowed to you. And there is a deadline. That means that if you submit a minute after the deadline, let's go. That's easy. That's usually for ALMA, for all easy thing is 15 minutes. That is what. So then there is another maybe couple of months where the TAC, which is the Time Allocation Committee, will go through the proposals and rank them by scientific merit. This is main criteria. And they will produce a ranked list of proposals. Then there is another maybe 3 months of technical things happening. So that the more technical people will take a look at the proposal and say, well, maybe this cannot really be done as they wanted it to be done. Before that? Oh, okay. So here, there is a pre.
There's a technical assessment and there's a scientific assessment.
Yeah.
They happen more or less at the
Okay.
same time.
Okay. So this is the time that it takes you to generate all the experiment, so all the scripts that are necessary to run the telescope as you want it to be run. Right? And then the 6 months mark, the window for observing starts, and it closes 6 months after. So you apply today, and the latest that your observations can be obtained, if you're lucky, get accepted and everything else, will be a year from today. Right? The various cycles overlap because you don't want to have a 6 months idle window, so that you have N+1 that will start 6 months after here. So here, when you're ready to start execution for those proposals, you ask for the new ones, and you evaluate, and you vote it through. And before you ask, I will get to the sort of mode. How is this done? And to do this, I think you have to remember a few things. With the space satellites, you don't even ask. You know what you have, and you work with it. Here, you can do a lot, but maybe not everything is always available. And again, this comes handy with comparison with big facilities. One is what we already discussed, and actually Valentin already said, if you want to distribute the light differently to the instruments, you have to move these beam splitters. These beam splitters are big. You know, this is the kind of size, and now I use 20 kilos each, and so you don't do that very often. It takes you a day to do it, and of course you don't want to waste a day every 3 days. So that any given configuration probably will stay in place for a month or something like that. And again, if anybody has any other experience, this is what you want. You know, the antennas are positioned like this for a month. Up to you, do you want it or not? You know, and so next month there will be different and so on.
So, Gianna,
Yes.
I guess then if for a month you have the same configuration, the proposals will be grouped according to what they want, right?
Correct. Indeed, I should have said this.
Can you repeat the question, Gianna?
Say what?
Can you repeat the question, please?
Oh, the question, she said that if the light distribution is going to be in a certain configuration for a long period, your proposals will have to be grouped within that configuration. You know, it's not just the best science versus the worst science, but there's also more granularity to it. Then you have to say, okay, this is the best science that I can do with this configuration, and so on. Yes, there is a lot of that. And one of the things that we're trying to do is also to establish which is the kind of configuration which is most requested. You know, so that we know maybe from the beginning what we can offer and satisfying a larger number of people. Yes?
There's no flexibility, let's say if you're interested in like transients or interruptions or something like that, there's
Not with the light distribution. I mean, by definition, really, that cannot be done that fast. No. So this is one thing that I don't know if you all understood the question. If you're interested in transients and whatever that might happen, you know, target of opportunity kind of thing, like a flare. One of the science use cases that we devised was trying to get, say, a flare science use case that could be good for multiple, for several light distributions, or for the ones that would be most used. So that there will always be something which is good to do if a flare occurs. Yeah, but there's a lot of these things that need to be defined, and we'll learn as we go, really. I mean, I think this is very different than how the telescopes nowadays, until now, is working. Of course, the seeing and the sky quality cannot be responding to what you want. Everybody wants this kind of images, but sometimes you get these ones, and this afternoon there will be, because I already know, discussing that. So that if you, use case, if your science really requires super high resolution, you might not run. And the idea is, well, I'll just leave that. Sometimes, though, you know, the seeing would be bad at some point. This is a plot from the DST, where the smaller this number, the better the seeing. So you see it gets better and better as you move into the day by an hour or so, and then it degrades. The good thing is that here, when your high resolution things cannot be done, would be around noon when you have the rest of the sky. So that is the idea that exists now, but will have to be verified, that you will do your highest resolution things a couple of hours in the morning and then move to chronos. And so on. So all of this put together coalesce into this fact that we will be using service mode extensively, because there is a lot of parameters that need to be taken into account. You know, you want that. If I give you the telescope for a week, you might get 2 hours out of it. I don't think we can afford that. It's not until the facility is 30 years old or something. And so the idea is to have a dynamic scheduling where you constantly update your rank list depending on the pre-filter configurations, the sky quality, the seeing level, and so on. And so you will not be there to keep things on the platform. Service mode and the coordination with other observatories is not trivial, but it is one of the things that we want to do. So coordinate, say, SDO, of course, everybody, it's always there. we don't care. But say coordinated with iris or coordinated with, if it's still up or something else. And that will have to be worked out. I don't know if we have any hard answers in this matter. Also because one of the things that we don't know yet is how the image quality is distributed during the day and during the year and so on. I mean, say with the DST, the SST, we have decades of operation and we haven't changed. Here we don't. I mean, we had the site survey that tells us certain things, but then we have to try and test it out here. And here, some fraction of the time, however, we offer in access mode because we don't want to discourage the people. We want them to go out there and see the thing and so on. But I put an XX here because I don't want to compromise myself for technology processes. So, and Valentin already talked about the Coudet lab being essentially a clean room, that there is a dust control, there is also thermal control. So the instruments are very temperature sensitive and you don't want to disrupt that equilibrium with going in and out and out. And I think that's about it. This is just one slide and this will be discussed on Thursday morning by the kids. So, if you guys have that more picture. Please register. Yeah. Questions?
Yeah, I have a question. I guess you were talking about the whole operation is mostly proposal driven.
Yes.
Like all the observation times for data products can be pretty much based on what scientific proposals we send in. Does that mean, like, say, if I just want to get a set of, say, photospheric or chromospheric magnetograms, I have to send in a proposal for that? Those are not going to be routinely generated?
I think that everything is proposal.
Can you repeat the question?
Yes, the question, sorry. The question was, it seems like everything is proposal driven. So if I am interested in something routine, like a set of photospheric or chromospheric magnetograms and so on, I still have to submit a proposal? And yes, the answer is yes. If you have in mind something which is more like periodic in nature, say like a synoptic program, even if it is a high resolution, you can certainly propose that. It's one of the modes that we will consider and do. Then there is also the issue that at some point there will be archival data that you'll be able to use. If I don't know how routine your things could be, like every quiet sun, any day, doesn't matter. But yes, the main guideline is that it is proposal driven. I saw another. Yeah.
So it was just going to say that after the embargo period, then the data will be available if you just want to be able to pull that from the archive.
Sure, that is true for most of the telescopes. That there will be an archive with hopefully easy to search, like the IRIS one and so on. Okay. Gianna? Yeah. They are on a fixed. Yes, are the beam splitters on a fixed mountain? I'm not sure I understand the fixed. There is a place on the table where you position the beam splitter. You can take out the beam splitter and put another one in there. The same. Is it a space issue? Yeah. It's rather crowded out there.
Gianna, it's possible to hear the questions
Yeah.
back here.
Okay. So beside he was questioning whether there couldn't be some sort of stages where you can slide in and out the beam splitters to change the light distribution. And the answer is really no. They have a fixed position on the table, but you put them in and take them out of the. maybe I can repeat what you said. So she is recording the building.
So I only wanted to say that the only exception to this is and that one is on stage. This one is loaded out.
Can you repeat that because the microphone is right beside you?
No, you need to go with the mic, I think.
Oh, okay. Well, essentially, the only time when you can do this sort of automated moving of optical elements is when you insert the feed mirror for trial, because there's more space for it. You had another question?
Yes, the temperature stability of the instruments. They are not temperature stable if it's wavelength.
Yes.
I just want to ask how stable are they?
Okay, so I know the number for the VTF. The question is how stable in temperature are the instruments. So the number for the VTF is 0.1 Celsius, 0.1 degrees Celsius. And I don't know exactly for the room what kind of number you're aiming to.
1 degree.
1 degree. So this is the general environment, is 1 degree, and every instrument might have their own temperature stabilization. VTF does for sure. Yes.
You had a picture of making the point that all the instruments, fields of view have to overlap. Presumably, correct me if I'm wrong, but in each instrument's head information, there will be pointing information to where you think within the overall field of view each instrument is pointing somewhere.
Yes. So, Alistair, here you might help me. The question was, I showed that all the field of views do overlap, all the instruments want to point somewhere, and he was asking that information will be in the header,
Right.
and it will be, how to say, individual to the instrument. I mean, I imagine that there might be some offset or something. Is that what you were aiming to?
How accurate is that?
Ah.
How can you test how accurate it is?
So how accurate is the position? I think that the pointing of the telescope in itself, you go overboard and there's going to be a little bit of one effect. The instruments one to another, I think that I would have to be find out.
Well,
Right, so?
there are.
Oh, that's right, so.
There are requirements to go to the absolutely relevant.
The blind point. I will repeat, yes, sorry, either you can, or I have to do this. So that the requirement for the blind pointing of the telescope is 5 arcseconds. So you say go there and you will go there by 5 arcseconds. But then there is a procedure that finds the limb of the sun, and that helps you in defining the pointing much better on the sun, and that would be by less than 1 arcsecond.
That's all I know. I don't have all the answers either, but so there was a 5 arcseconds line and then there's a limb finding algorithm which probably will be down to an arcsecond less. Maybe then there are a couple of other things we will be able to do, but it's
It's always just wondering where the target opportunities are actually available. So if you have obviously the whole specific where you make a developments, someone is getting your data recorded and you want if there's similar examples, you just go about and you all plug there. Or is there
You cannot change the configuration much, I mean, unless it is,
well, you can move the point. It's not so much the configuration, just that I'm more curious about the options and flavors the priority for the observations that are taking place?
Okay, the priority I think should be settled after the fact. Level when they say, okay, this is a valuable opportunity. If there's any happen, yes, go and observe that. How this is implemented in reality, I think that will have to be discussed, and it would be a good idea to maybe put a question to the guys. Personally, that is there often. I don't like moving my telescope and going to something that is already there because I'm missing most of what I
Yeah.
Right, although there might be some legitimate science reasons to do so, you know, I don't want to observe the phase, form, this or that, or whatever. So I think that should be maybe specified in when you define the observation as a capital of it. Like it happens in another region, that means moving over there, you know, once. I think that there have been some fair related workshops and discussions, and the consensus was more like, let's take where we are.
Yeah.